of theorem 2.1.1. Just as said, this theorem gives you a necessary and necessary and sufficient condition that to check whether a counting process should be Poisson. All right. So so now the forward direction. So here I will assume that this counting process is some process, and we want to prove the four properties here. And recall that our definition for some process is that that n0 is 0 will be 1, and the second thing is that the counting process has independent increments. And the third thing is that the counting process has stationary increments, so that the distribution of any increments is Poisson with parameter lambda times t, and the lambda is the rate of the Poisson process. So now we have these three properties. So so now the first property, 1 is equivalent to the Roman 1. Okay, you can see that. So that data actually here. And also the second and third property implies the Roman number 2, because Roman number 2 stay here, and P has independent and stationary increments. So I think given that the counting process is Poisson, then the Roman 1 and Roman 2 are satisfied. So what we have to do is to prove Roman 3 and Roman 4, right? Okay, so now we have to use the property 3 for some process. Okay, now we know that so NH is the increment, right, in the time interval from 0 to h, right? So that this random value n of h is a Poisson distributed with parameter lambda times h. Okay. So according to the Poisson distribution, that this random variable has value 1. So this event occurs with probability equal to this expression here. Okay. And so that so you can see that this we can express this term we can express into two terms. And look at the second term. We claim that the second term is a little O function of h. Okay, so to check whether this term is the little O function of h, we just divide the function by h. Okay, and let h goes to 0. All right. So you can see that because as h goes to 0, both the numerator and the denominator, right, goes to 0 too. So by L'Hopital rule, you can take the derivative of the numerator as well as the denominator, right? So once you take the well, maybe I do it for you here. So limit. Okay, so limit. And the derivative of the denominator is 1. Right. And right, the derivative of the numerator, I think this term, we first take the derivative of this one, plus the derivative of this one, and the derivative of this one is minus h. Okay, and minus lambda. Right. Now, so as h goes to 0, this term goes to 0. Right, the difference goes to 0. And over here, this goes to 0. Okay. So we check that this term, the second term, is a literal function of h. Okay. So that we have that one. Okay. So the probability of this event is equal to lambda h plus the literal function of h. Alright, so this is just Roman number 3. Okay, so proof. Again, by property 3 of the Poisson process, the probability of this event actually is 1 minus the probability of this event and minus the probability of this event. And we know that n of h is time distributed, so the probability of this event is equal to e to the minus lambda h. Okay, we know that. And this term has been proved, just proved here. Alright, so that we have this one. Alright, so now our purpose is to prove that this probability is a little function of h. Okay, so little function of h. So now we just check whether the limit of this ratio goes to 0 as h goes to 0. Right? So once again, we know that if h goes to 0, this is 0 and this is 0. Okay, so the numerator goes to 0 and the denominator goes to 0 too. So we have to actually check the logical form. And well, okay. So we have to. Okay. I think I have to skip a little bit. Because you may think, but I have to take a derivative of a little or h function. Actually, it is not necessary because okay, and we have shown that this is 1 minus h. Right? And minus little h. But minus h you can change the class because minus little or h function is also a little h function. So I just put the class on here. And so what I need to do is just to compute okay. But by the definition of little function, that this is goes to 0 already, so we don't need to check that. Okay, so the second term goes to 0 by definition of little h function. So what we need to check is this one. Okay, that's why I just because this is go to 0, so I just okay. Okay, and this is already 0, so that we can omit it. Okay? Okay, so because there are something happened here, I just skipped it. So, okay, so we have to check only the first ratio here, and by logical laws, we can take the derivative of the denominator as well as the numerator. So this is 1, and the derivative is this one. And of course, as h goes to 0, this goes to 1, and so the difference goes to 0. You get the 0 here. Alright, so no problem. We have the conclusion that we have this result, and which is just Roman 4. Okay. So that by assuming that NT is a Poisson process, then we have these 4 properties. Okay. So now the reverse direction is a little bit difficult, isn't it? So we have to put, assuming these 4 Roman properties, then we have to prove that NT is a Poisson process. Alright, so this direction. Again, okay, number 1 is equivalent to numerical property 1, so no problem with that. And Roman 2 says that NT is independent increment. So of course, property 2 just say that HG has independent increment. All right, and so we have to, and the stationarity of NT implies that so that what we have to do is to prove that NH. So what we have to do is to prove. Sorry. Okay, is to prove that because that Roman 2 says that NT has stationary increment. So there's no problem that the distribution of the increment will not depend on T. Okay? Will not depend on S. So just depend on T. And we have to prove that the increment has this Poisson distribution. Okay, that is the key, right? So we have to prove that we have Poisson distribution. Starting from Roman 3 and Roman 4. So with Roman 3 and Roman 4, we have to prove okay. Now, the stationarity, all right, the stationarity of NT claimed by Roman 2 tells us that the distribution of this increment is the same as the distribution of T. Okay. Right. So that is the starting point. Now relate this probability. Okay, as P and T. So it depends on N as well as T. So we have that. And for all T greater than 0 and non-negative integer, right? There. So this is the starting point. Okay, so we first consider N equal to 0. Alright, so what is P0? So P0, T plus H, P0 T plus H, it is the just the probability of this event. Okay, so we have that. This is the time. This is time 0. This is T plus H. Okay. So it says that up to time T plus H, there is no arrival. The coming process is 0. Okay. So that means that up to time T, there is no arrival. And in between T and T plus H, there is no arrival. So this event, this joint event is equivalent to this event. Now because that but NT and this increment, they are independent because we have independent increments, right? So the joint probability becomes to the product of the probability of each individual event. Okay, so here we use independent increments assumption, the Roman 2. Okay, so we use the independent increment. And exactly, this is our definition of P0T. Okay, so this is P0T here. And what is that? By the stationary increments, alright? This increment is the same as NH. Okay, so h is equal to 0, right? That. Now, but probability of this event is equal to 1 minus probability that the NH equal to 1 and minus the probability that NH greater than or equal to 2, right? By the total probability theorem. So we know we have that. Alright, but we have some information about this probability and this probability from Roman 3 and Roman 4, right? So here is that okay. So this is the minus h, right? This probability is lambda h plus a little o function, but this is a little o function. So the sum of two little o function becomes to another little o function, right? So we have that. So this term becomes 1 minus lambda h plus the little o h, right? And so we take the difference because that see here. So we take the difference, and the term is here. It's lambda h times p0 t, okay, and little h 1. Because we are, when fixed t, this is a fixed number, so a fixed number times a little h function of little o function of h is also a little o function of h. Okay, because we can think about that t has been fixed. So that. Okay, and then we take the ratio, yeah. Okay. All right. Now, as h goes to 0 from the right hand side, okay, as it goes to 0 from the right hand side, the one-sided derivative exists. Okay, the one-sided derivative of P0t exists, and which is equal to this quantity. Okay, so from Roman 3 and Roman 4, we proved that P0t has right-sided derivative for all t greater than 0. So from the right hand side, you have right-sided derivative. Any questions? Okay. Now we have to check whether the left-sided derivative, whether left-sided exists or not. So we have to check that. We'll consider h less than 0. All right. So we approach h from the different side of 0. Okay. So h is negative. H is negative. Okay. And for all t greater than 0, all t greater than 0. So this is very important because if t equals to 0, there is no definition of n of t for negative t, right? So we have to think about that. And so that similar consideration, I just omit the process, the details. You can follow a similar argument here, okay? But remember that h is less than 0, so the time, this time is before the time t, okay? Before the time t, so that the situation, you draw the line here, you have to see that this is t across h, okay? Because h is less than 0, okay? So when you use the independent increment, you have to consider the increment from 0 to here, this increment, and this increment. Okay? It's a little bit different. But the idea is what we said as we did here. Okay, so end up with that we have the same result. Okay? So that we know that the P0t as a function of t has derivative for all t greater than 0, because they are the left-hand side derivative and the right-hand side derivative are equal. Okay, and so and this one, okay. And also the derivative can be here. So and the initial condition, we know the initial condition here. The initial condition is that, by our definition, I'm sorry, I have to put 0 here, because it's t equals 0, right? So, I have to keep this. Alright. Alright, so please correct it. This is n0. But n0 equals 0 is for b1 by Roman 1, right? Already, this is our assumption. So with initial condition with this one and with the and actually this is actually, if we have to see that this is the exponential function, right? Exponential from calculus. So of course that this is the exponential function here, all right? And the constant equal to 1 because of this initial condition. So that so this is the solution here. So first of all, we determined that P0t is an exponential function for all t greater than 0. Okay, and by the continuity at t equals 0 with this initial condition that we actually we can put an equality sign here. Okay, so now we already solved the problem. Okay, so we already solved the problem for n equals 0. N equals 0. So now we have to consider, all right, n greater than or equal to 1. Okay, all right. So now. So we hope to use the induction, right? So that so here again h greater than 0. So our time diagram is here. T is here. T plus h is on the right hand side of t. Right. So the idea actually is almost the same, right? So that well, in this time interval from 0 to t plus h, we have n arrivals. And n is greater than or equal to 1, so at least one arrival there, right? At least one arrival. Okay, so there are some other things that well, you can think about that all the n arrival will be in between 0 and t, and then the rest in this interval has no arrival. This is one condition, one possible condition. The second condition is that well. From 0 to t, we have n minus 1 arrivals. Okay, and the rest is in here. Alright? And etc. So we can divide the event into several small events. Alright? So here is that from 0 to t, you have n minus 2. And the rest is in this interval from t to t plus 1, you have. So in general, if in between 0 and t you get n minus k arrivals, then the rest of the k arrival will be in this interval. Alright, so you sum of them. So actually you partition the event into how many events? You partition them into well, n plus 1 events. And all these small events are disjoint with each other. Alright, so that by using countable additivity of the probability measure, just add the probability of each individual event up we got to this the probability of this original event. Any idea? Any problem? Okay, so that is obvious. All right, and so again we can apply the assumption of independent increments, right? And so here is the so now we estimate this one. Well, so you can see that when we estimate that, because the joint event here is upper bounded by because that the intersection of these two events is a subset of this event. All right. So the probability of this event is greater than or equal to the probability of this joint event. All right. So we have upper bound here, and together the sum together actually is the probability of the increment has greater than or equal to 2. All right. The value of the increments is greater than or equal to 2. Okay. And by stationarity of increment, you get that. And finally, by increment for this term, actually is little h. Okay. So we first estimate the sum here, this complicated sum. And we find that this complicated sum is just a little function of h. Okay, it's a little function of h. So that's fine. Okay, and then we estimate the rest two terms. The first one is that when all the n variables is in between time 0 to time t. Okay, and again by independent increments assumption we have that. All right, and this is PNT by our definition, and by stationarity of increments we have this probability is equal to this probability, and again we use normal number 3. Okay, so we have that. And how about this one? Again, well, we have so this is normal number 3. Actually, this is normal number 3 and normal number 4 because we already find what is that before, right? When we consider P0 at t here. Remember, right? We encounter the computation of this probability, and this probability is equal to 1 minus lambda h plus the little h function of h. Okay, so that is here, and we directly apply the normal number 3. So this is lambda h plus or h here. Okay, so we know how to express these n plus 1 terms. And so the result here is that we end up with an equation that PNT plus h is equal to PNT minus lambda h PNT plus lambda h p minus 1t, and a little h function. Okay, and also so we use the same technique, okay, to find out the ratio and also this ratio. And by taking h go to 0 from the right hand side, right? From right hand side, we find that the limit exists. The limit exists, which is equal to this sum. Okay, for all t greater than or equal to 0. All right. So we know that Pn of t has right hand derivative. Right. And similarly for h less than 0, we can prove that. We can prove that the left hand side derivative also exists and equal to the right hand side derivative for t greater than 0. Okay, so we establish a differential equation again, right? So we have established a differential equation. But this differential equation involved, so the derivative of PNT is a function of PNT as well as Pn minus 1t. Okay, so and so that we can simplify this differential equation. This is the first order differential equation, right? And we find that if we move this term to the left-hand side and multiply with the differential function, multiply with that, okay, we find that actually the differential equation becomes to be much simpler. Okay, so you can see that. This is just somehow. Well, you know, if you have the experience in solving differential equations, sometimes it will be useful to multiply something. Okay. Actually, it is called the integrator method. But anyway, yeah, I think you know some of the techniques there. Okay, so this is one of the techniques we used in solving differential equations. And so we have that. So we have things becomes to much more simpler, and so that so for example, when n equal to 1, when n equal to 1, all right. So the derivative of this term is equal to lambda e lambda t p0t. But we know p0t. What is p0t? P0t is just the exponential function. Yeah. So this is constant. Constant. And then it's quite easy, right, to solve it. So we have that, and then Q1t is just here, all right. So K is the constant we have to determine with the boundary condition. Okay. So what is the initial condition we have? Yeah. Is that for Pn0. Pn0 is just the probability of this event, right? It's 0 for any n greater than equal to 1 by Roman 1, right? By Roman 1. So we know this is 0. Okay, and from that we can see that so this boundary condition determines that the constant k to be 0. Okay, so well. Okay, so that when t is 0, so this is 0, this is 1, so k equal to 0. Okay, so you can see that k equal to 0. Right. So now k equal to 0 and Q1t is just lambda t e to the minus lambda t for all t greater than equal to 0. Okay, we incorporate the initial condition here into the solution. Okay. Just like I think I mentioned that when we solve P0t, we have to put quality here, right? To incorporate the initial condition. All right. So so we have now. So now we have that, and then we can guess. We can guess that the solution should be a function like this one. Yeah. Because from P0 and Q1t we guess this one, and this can be proved by induction. Okay, by induction. Yeah. So the proof by induction is quite easy. So I just you try. If you have problem to prove this claim by induction, let me know, and I will tell you how to prove it through the email. Okay. So this, and so for given fixed time t greater than equal to 0, we have that, and this is exactly the Poisson distribution with Brown. So that. Okay. So from the proof, you can see that the point is okay in the statement here. Norm 3 and Norm 4 give us this situation, the conditions that we need to establish differential equation. Okay? To establish the differential equation. And so from the differential equations, we can solve it and find out our distributions. Yes?
What is the relationship between independent increment and stationary increment? Because we use it, always use it in the proof.
Yeah. Well, there are two different assumptions.
Yes,
yeah.
But how can you put it in like this one? Why can it becomes this?
Oh.
Because this is
increment, yeah.
And this is stationary. Why can we put equivalent?
Well, yeah. Okay, so let me, I know your question here. Okay, so okay, particularly here. Right. So we have that, right?
Yeah.
So this is the first increment.
Yes.
And this is the second increment.
Yes, I know they can.
Yeah. So we have that, right?
Yeah.
And then this increment. This increment is the increment in an interval of length h.
Yeah.
Because the length is h. So that this random variable, okay, has the same distribution as nh, because nh is from 0 to h, from 0 to h.
Oh, okay.
Yeah. Other questions? Yes, it's a case of that. Yes, that's right. Because that for stationary increments, any increments corresponding an interval, for example, if the length of the interval is h, and we arbitrarily select an interval of length h, then the increment in this interval has the same distribution as the increment in this interval. It is called stationarity. Okay, so that is so I think this theorem is the most fundamental theorem in the theory of the Poisson process, and from the proof you know the flavor of the properties of the Poisson process. Okay, so now once we have these fundamental properties, okay, so we now examine some deeper insights of the Poisson process. Right? So we will describe the Poisson process in terms of arrival times and the inter-arrival times. Okay. So again, the background is that for any random experiments we have associated some probability spaces. So suppose the omega is an outcome of some space. Okay, and now for the point process that the Sn omega is the arrival time of the nth event. Okay, but for this outcome, because for an outcome you have the time arrivals of events, and this is just the nth arrival, the arrival time of the nth event. And we define the difference between the arrival time of the nth event and the arrival time of the n-1 event. And so you can see that the difference becomes to the so-called inter-arrival time between the nth and the n-1 event. Okay, so here, okay, the S1 can be, think about that it is the inter-arrival time between the 0th event. We think about this one event here, and this is the time. Right? S1 omega is the time, the arrival time of the first event. So that we wait for not long, right? Not long for the first arrival. And to wait for the second arrivals, you wait this time interval, right? So the length of this time interval is x2, right? Which is the difference between s2 omega and s1 omega, etc. right? So we can describe the point process in terms of interrupt times. And so that okay, and remember our point process, the arrival times of events has order, right? And by our definition of arrival times, we know Sn actually is the sum of the previous n interrupt times. Okay, so we have the relationship. So once you know S1, S2, S3, etc. I'm sorry, this is Xn. Okay, another type of errors here. So if we know the arrival times, then we know the interrupt times. Conversely, if we know the interrupt times, then we can know the arrival times of the nth event. Right. So the description of point process by arrival time is equivalent to the description of the point process by interrupt time. So they are equivalent to each other. They provide the same information about this London phenomenon. Okay? Any questions about the definition of interrupt times? Okay, good. So, so now we recall that if Y and Z are statistically independent, then we have this one. The conditional expectation of Y given Z actually is just the unconditional expectation of Y. It's for V1. Okay? So as a consequence, for any Fourier metrical function of Y, okay, with a finite expectation, then because this is the a function of Y, so that that Fy and Z is also statistically independent, right? So Fy and Z are also statistically independent. Do you have any questions about this? I just say that if Y and Z are statistically independent, then Fy and Z are also still independent. Any questions about it? Maybe I can reinforce your memory here. Our definition is that so two random variables are statistically independent is defined that if we take an event from the sigma algebra generated by X, means that if we take an event which is defined through the X, and if we take an event F defined through Y, then the probability of their joint event is equal to the product of the respective probability, right? So that is the definition here. Okay, now, because that we have proved that f of Y, okay, we have this result, right? For any Fourier function of Y, okay, the sigma algebra generated by this new random variable is contained in here. Because the f of Y is a signal process Y, so it's a process Y, so it contains less information. So that we have that. And so from that, so we know, so X and f of Y are statistically independent. Right? If you we will think about another g function of x of course you have that, so that you can extend the result that any function of x and any Borel measurable function of x and any Borel measurable function of y are statistically independent. Okay, so we have that. Okay, so in particular, if we consider the conditional probability of this event given z, the conditional probability of this given z can be defined through the indicator function. So this is just a conditional expectation of the indicator of this event, right? Given random variable z. Okay. And you can see that when y and z are statistically independent, then we know this is a Borel measurable function of y. So this random variable is also statistically independent of z. Okay, and then the conditional expectation given z becomes to be unconditional expectation. But the unconditional expectation of this indicator is just the probability of this event. Okay, so that you have that. Any questions about these expressions? So, conditional probability given a random variable actually is a random variable and it's a function of z. Through here, you can see that. But this random variable actually is a constant with probability 1. When y and z are statistically independent. Okay. The converse is also true. If this is true for all Borel set, then y and z are statistically independent. Okay. So here is the proof here. So now we can just check. We check the Borel set. We check the Borel set only for when b is equal to say just a semi-infinite interval. Okay. So is that so? So that is that y is in this event is just equal to, right? So there are quite a few different notation for the same event. Alright, so we suppose that we have this property given two random variables, and we know that this is true. Okay, this is true. Then we will show that y and z are statistically independent. And to show two random variables are statistically independent, we know we have a theorem that says that the joint distribution of y and z is equal to the product of their marginal distributions. Okay, so this is what we want to see. So we want to prove that the joint distribution of y and z is here. Okay, and so that so we can again I skip one step. So let's see. Okay. So this is actually okay. So that the unconditional joint probability can be expressed first of all, you can condition on Z and then take the expectation. Okay? But if you think this is hard to realize, then I can go through another way. So this is the expectation of indicator of something like right. So this joint probability is equal to the expectation of the product of these two indicators. Okay. Two indicators.
When you write like this, you already split Y and Z as dependent.
Yeah, but you can prove that directly. The joint event, right? When you express by indicator becomes the product. Okay, it's a common practice, you know. In probability theory, we quite often use this property here. Let me show you. Let E and F be two events. Okay? So if we want to find their joint probability, it's equal to the expectation of indicator event times. Why? Alright, we compute that. We can give a proof. We know this is the definition of indicator, right? Okay. So the product. Check the product, the value product. So that is IE times. Okay. And we notice 1 or 0, still two values, right? Either 1 or 0. And when we have 1, when omega is in the intersection, right? That's why the intersection comes into the arena. Only by product, right? Only by take the product of these two indicators, then the intersection will come to play a role here. That is the key observation, okay? And 0 otherwise. Okay, so now maybe I save my space here. So the expectation of 1E, 1F becomes to 1 times the probability of E intersected, right? Because when the value is 1 when omega is here, so that still faster. I slow down myself, okay? Okay, this is by definition. Because this random variable is two value, 1 or 0, right? So it's there. But so this is probability of. Okay, but from our discussion here, we know that IE, IF, the product equal to 1, if and only if only that the outcome is in this section. So this event is actually since the event equal to and so now y is equal to 1 z. This event, okay, is equal to the indicator times the indicator equal to 1. I use indicator because indicator are random variables. Okay, so now the intersection of these two events is equal to the product of their respective indicator equal to 1. Because this is E. Okay? And so E is here, right? F is here. Okay, so this is the indicator. So the product of these two indicators equal to 1. But what is that? 1 and 0 seconds. Okay. So that is when y so omega is in here means that the value would be less than or equal to 1. So I just put that. And so this actually is an indicator of, right? From that, okay, and so this is of 1. So this function, so now I established that, so my conclusion is that the indicator of this event actually is a function of y. What function? Is this Fourier metrical function of y. Okay? So the indicator of this event, because this event is in what? Is in the single echelon. But because the event is defined by y, right? So from this calculation, we find out that actually this is an h of y. And what is h? H is a Fourier metrical function. The h is from h of x equal to 1 and 0 is x. Okay, so h of x is an indicator function of the interval. So h of x is 1 when the element, the point is in this semi-infinite interval, and 0 if x is not in this semi-infinite interval. So it is a parametric function. Probably I'm so familiar with this language, so whenever I look at this indicator, we know it's a function of y. Because it's used here. It's a function of y. And so now, so now this event becomes to so the event is like this one. Okay, so the probability. Okay, is the probability that okay, so this jump probability actually is the probability that the product of these two functions equal to 1. And so this is disputation of disputation. So the joint probability equal to the explication of these two functions, y and z. Alright, and so by conditional expectation property, given z, alright, and then take the expectation. But now this one is a function of z, right? So by theorem 1.2 point, I think is 8. Yeah, it's 8. So I can move this out of the condition expectation. So this is expectation. Okay? So I can move it out of the this is condition expectation by this is because by theorem 1.2.7, okay? And this is by theorem 1.2.8. Okay, and so we now this is here. We now is here. Okay. So from here to there are some stories. Okay. Because that this is actually is this y this and y. So and this is probability that So this conditional expectation is the same as this conditional probability. The reason is the same. You can derive it separately. Alright, so this is our starting point. Yeah. Okay, so this is a function of z. This is also a function of z, right? So the product is a function of z. You take the expectation. So you have to do the average. So the average is that the expectation is that you take the Riemann's teacher integral. So the integrator x f of z is the CDF of z. Okay, so because this is a function, right? A function of z. So that you have that, and then where this indicator function contributes the interval from minus infinity up to theta z. Because initially this is from minus infinity up to infinity, and then here we have an indicator function. So after observing indicator function, we have this integral. Okay. And again, because y and z, by our assumption here, right? We assume that this is constant, and so we can move it up here. It's a constant, right? And so, but this is the integration of the CDF. So this is just equal to the probability that z less than equal to z. And we have that. This is the joint distribution, and this is the product of the marginal distribution. So that shows that z, y, and z are statistically independent. Okay. Any questions? You can think about this as a review of what we have done before. Okay, so the proof give the answer, right? The answer is yes, and we know that. So this one is this statement. If this is true for all Fourier set, this is much more stronger than this one. But eventually, it seems stronger, but actually they are equivalent to each other. Okay. So because we use only the Fourier set, which is equal to this semi-infinite interval. Okay. So now, we have another description of Poisson process in terms of interval terms. Poisson process with rate lambda, for a Poisson process with rate lambda, the interval terms x1, x2, etc., etc. Because Poisson process is a special kind of point process, right? And so it can be described by interval terms. But for Poisson process, the interval terms are independent. So x1, x2, they are all independent and identically distributed. So they are ID. And furthermore, they are exponentially distributed, right? With parameter number. That means that each xm greater than t, the probability of this event is e to the minus 1 t. So that the interval term has probability density function. Alright, this is a density function for all t greater than or equal to 0, and it's 0 for t less than 0. Because interval term is non-negative value. Alright, so it shows that for a Poisson process, because it's a special kind of counting point process, and we find that for a Poisson point process that the interval terms are very special because they are independent, identically distributed, okay, and exponentially distributed. Any question about this statement? If now, so we can go for approach. First of all, we compute a version of conditional probability of the event given x1. x1, what is x1? x1 is the first interval time, and the s2 is the second interval time. So here is the okay. So x1 is the first interval time, s2 is the second interval time, and our purpose is to prove that interval times are statistically independent. Okay, so the first thing is we want to prove x2 and x1 are statistically independent. Okay, we want to prove them. And what we want to prove, we can use the property I just said here. That if we can prove, we can show that this conditional probability is equal to the unconditional probability. Then x, y, and z are statistically independent. We have shown that, right? So this is what we have here. And so we will, but this time we use the complement of the from, because this is a complement. We know that the complement, right? We just consider, but that's fine. Okay, because it's much more easier to deal with the complement. All right, so we consider the conditional probability of this event. The event is that the second interval time is greater than t, greater than some t, given s1. And of course, this one, a version of that is a function of x1. So we try to want to guess or claim or find a version of this conditional probability. Right. So now this is a technique, right? And use the many cases so you can learn from them. We consider the joint probability. So this is the event, right? This is another event. Remember, the interval time usually continuous random variables. So to have a good event, we consider an interval, even though it is quite small. For example, delta s may be very small, tiny number, but eventually, but no matter how small it is, that is still an interval. Okay, and so usually this event has positive probability. This is what we want. So that okay, and we select the delta x smaller than t. Okay, smaller than t. Right, and s greater than 0. So we have the situation that the interval time is about equal to s. Okay, but here when we say x1 equal to s, the probability for x1 equal to s, usually for continuous random variable, the probability is equal to 0. Right, so we have to avoid it. Right? So that's why we consider a small time interval. But roughly, you can think about that x1 is approximately equal to s. And this is another formal way to say that informally, s1 is equal to s. This is informal language to say so, but rigorously, you have to say it in this way. Right, so now we compute the probability. Okay, the joint probability here. Okay, again, whenever you encounter an event, you turn it into indicator. Okay, because expectation is much more easier to deal with. Okay, so we turn this probability into an expectation. of indicators. All right. So here, this event is represented by here by a function of x1, x2, and also this is a function of x1. Okay. Going by doing, so this is the indicator of this interval is a parametric function. The indicator of this interval is also a parametric function. Oh, by the way, oh yes, good. First interval. So we have that, right? And then we use the conditional expectation. All right. So this is by using theorem 1.2.7. Okay. I forgot to put another bracket here because this bracket corresponds into this one, and this bracket is no counterpart. So we have to put another bracket here. Sorry. And by theorem 1.2.8, because this is function of x1, so whenever you condition on x1, you can move the function of x1 out of the condition expectation. So we have that. Okay. Okay. And then now we have this one. So this condition expectation becomes condition of probability. Right? And by so this is actually the integration, because that well, so now this is a function of x1. This is a function of x1. Okay? Right? This is a function of x1 function. So when you want to take the expectation of a function of x1, right? This is the expression. Right? This is the integrator is the CDF of x1, and you put the function here. But the indicator function of x1 limits your the integration interval from s to s plus delta s, and this one is here. It is the so it's a function of x and of x1. So that it's a so when you let x1 equal to by the parameter u. So this is the condition probability you have. So from here you get that. Okay, and this exception will give us some insight to find out what is this function. No, it is a function of u. Okay, this is a function of u. Now, x1 is greater than s. The event, when we say x1 is greater than x, means that if x1 is greater than x, that means that this point, s is here. Right? So if this is greater than x, then s is here. So that means that from 0 to s, there is no rival. Okay? So that this event is equivalent to n of x equal to 0. Alright? So we know that the probability of this event is equal to the probability of this event. And as we know, n of s is some distribution with time parameter lambda s. So that when it's equal to 0, this probability is just equal to this number. Okay? So we know that this number, this problem is that. So, right? So once we know that, we know x1 is exponentially distributed with parameter lambda. Okay? Because when we know that the exponential discrete function, exponential discrete random variables, that so that this is equivalent to saying that the probability of x1 greater than x is this number. Okay. So once we know that, then x1 is exponentially distributed with parameter Okay? I think you don't have any question, right? Because as we know, this is probability S1. So this is 1 minus probability. Okay? And this is 1 minus. Right? For all x, we have that. And this one. So this is the CDF, right, of an exponential discrete random variable. Okay, this is CDF. Okay. Right, and so DF x1 u becomes to lambda t minus lambda s and the dx. Okay? So the equator comes to this equator. That's okay for you? Alright, so that this expression, what we have get is here. Any questions? Okay. So now we observe that this is our situation. And S2, now we compute the event that S2 okay, S2 is greater than T, and S1 is in between S. So this is X, and this is X plus delta X. So that for S1 omega equal to S plus delta. So we have that. So this is the time that the first arrival, and so we can see that ns equals to 0, no problem, and ns plus delta x. So the increment here, the increment in the interval S to S plus delta x is 1 arrival. Okay, we have 1 point. Why? And because S2 is greater than T, so the second arrival. So from here is S plus delta, go to S plus T plus delta here. In this interval, there is no arrival, right? Because the second interval arrival time is greater than T. So this is the first arrival time. So you have to wait at least the T times, right, to get the second arrival. So up to wait T times. So you now at the time S plus delta plus T. At this moment, there is still no second arrival. So that means that in this interval, there is no arrival here. And the situation, because it will assume T is greater than delta S, so that the time will be in this is here. The situation is this is S plus delta X, this is S plus T, okay, and this is S plus T plus delta X. So again, this time point is in between S plus T and S plus T plus delta X. So you have the time diagram like this one. Alright, so this event implies that you have this event. So this event is bigger. It's bigger because any omega, any outcome belongs to this event, then will belongs to this event. So this is bigger. This is bigger. Okay. Conversely, that if we have again this is 0 up to here, there is 1 here, and in between s plus delta x up to s plus t plus delta x up to here, there is no rival. Then, of course, the second order term will be greater than t. Yeah, because when you wait up to this point, there is no rival. You can see that the second order term, the second order term will be greater than t. So this event is smaller than this event. Okay. Right. So I have a bigger event than this one, and I have a smaller event than this one. Because that the probability of this event is hard to find. Okay? So that we use upper bound and lower bound. Okay? So that's why I have the time diagram here. So when I have a time diagram here, now we have the, so this is the probability. Okay, this is the probability. The probability of this event is less than the probability of this event. Yes. This one or this one?
This one.
Yeah. This one. Oh. Okay. Because that the first order term is here, and you are saying that the second order term will be greater than t. So from here up to this point, there must be there. We don't have any rival in between these intervals. Otherwise, if you have a mark here, then the interval term should less than t. Right, and so that when we consider from here to there, because the s plus t will be less than s plus t plus delta. So in this time interval, there is no rival. So I put 0, 0 here. The reason why I want this event is because I want to use the independent increments. Okay, the assumption. So the probability of this event will be less than or equal to the probability of this event. But the probability of this event is much more easier to get, because that it is the probability of this event is the probability of this event times the probability of this event times the probability of this event. Okay, and so that is here.
Could you go back?
Yes.
For the second one. Also the last one. Also the last one.
Oh.
Y is equal to 0. Maybe x2 can happen.
No, yeah. So that this one is more severe than this one. Because if this happened, then this must happen. This is much more strict. Mm-hmm. It's more strict than this one. Okay, it's more strict. So, but again, we have independent increments. Okay, so what we have is that we have only increment, independent increment and stationary increment, and then the increments has some distribution. That's all we have. And so, but this, the probability of this event is very hard to find. Very hard. So we use upper bound and lower bound. And so the upper bound, the probability of this event is here. So this is so that so we use the independent increment, right? And we know that because we know the distribution, we know that the increment has Poisson distribution. Right? So that well now we have upper bound and lower bound. Okay. So when we have upper bound, lower bound, and we divide it by delta x, and we take the limit as delta x equal to 0. This is what we have. Okay. And then so the limit here, this limit, okay, is that. Okay, so the limit, so you can see the limit should exist. Why? Because the upper bound and the lower bound are the same, right? They are the same. They are the same, right? So it pushed that this limit exists, and this limit actually is equal to when delta is equal to 0, then that u will go to s only, right? So that we find that this is the probability. Okay. Okay. So so this is one, and so this limit is equal to this one. So now we find the conditional probability, right? Because we established identity. So now, okay, so we have that. Because that this expression is equal to this one. So when you cancel, you find that this is equal to this one. Okay. And it's very interesting that the result is that this version is independent of s. Okay? It's independent of s. So it's a constant function. Because this is a variable function of s, right? But it turns out that it's a constant. It's constant. So therefore, we will prove that. We prove it's a constant. So that x2 is exponentially distributed with parameter now, and it's also independent of x1. So at the same time, we prove that S2 and S1 are statistically independent, and X2 is also exponentially distributed. You may ask, why this time you use greater than t? Because in our proof, here, we use less than or equal to 1, right? But this is equivalent. This is true if only if probability okay? The set. Yeah, that's it. Okay, because that because this is 1 minus So even though we we are given the condition, actually they are equivalent when we consider y greater than b to y. Okay, so now we have shown that x1 is exponentially distributed with parameter lambda, alright, and also is independent of x1. Okay, so up to now we know x1 is exponentially distributed with parameter lambda, and now we show x2 is also exponentially distributed with parameter lambda, and x2 is independent of x1. Up to here. So the same idea can be used to prove the general case that x1, x2 are independent and identically distributed exponential random variables parameter number. Okay, right, one by one. So you can show that it's the similar idea. So I think the point is that the proof I gave here is a rigorous proof. Okay, it's a rigorous proof, and so that's why I need this time diagram to explain everything. But the key idea is that to use the independent and stationary increments, always use these two assumptions. Okay, so now we have this wonderful property that that for Poisson process with rate lambda, the interval terms are RID and exponentially distributed with parameter lambda. Okay, now we go back to the rep term. We know the answer rep term is the sum of the interval terms, and we already know the xi's, the interval are RID, so they are independent. So if you want to know the distribution of xn, then you can apply the result in elementary probability theory. Okay. So here I just show you that there are a couple of ways to compute the CDF of xn. One is from the moment generating function. Okay, the moment generating function for the unsolvable term is defined by as an expectation of the exponential function of xn. Okay, this is the traditional way to define the moment generating function. Okay, and so this one is and because that xn is the sum of xi, so the exponential function of a sum becomes to the product of exponential functions. So this is btx1, btx2, etc. So now this is the function of x1, this is the function of x2, etc. This is the function of xn. And because x1, x2 up to xn are statistically dependent, so their functions are all statistically independent. Okay, and so that the expectation of their product becomes to the product of expectations. Okay, and so we have that. And finally, this is very easy, right? It's the nth power of the moment generating function of x1. And we know the moment generating function of x1 because x1 is exponentially distributed. So that this is the moment generating function of exponentially distributed random variable. Right? It's very simple. It's lambda divided by lambda minus t. Okay. And so that the moment generating function of xn is equal to this quantity. Now with moment generating function, we find that this is the moment generating function of a gamma distribution. Okay, a gamma distribution with parameter n and lambda. So in elementary probability, we establish tables, right? Tables between distribution and the moment generating function because they are one-to-one. pair 1 to 1. So once you are given the modular function, you know what is the corresponding CDF, or even know the PDF if it is absolutely continuous. So we know from that, we know Sn, the nth arrival time is a gamma distributed random variable with parameters named number. So this is one way to solve. The second way, I think I let you to go through just some computations only, right? So I skip their computation. So now the remark is that the remark tells you a converse result, because in the previous theorem we said that once we have a Poisson counting process, then the interrupt times are ID with exponential distribution. Conversely, suppose that we have a counting process, or we have a point process, and such that the interrupt times are IID and exponential distributed with parameter number, then the associated counting process is a Poisson process. So that so they are equivalent to each other. Okay, so they are equivalent to each other, and so you can so you can see that how to check, make a remark to check. For example, to check that n0, right, equal to n, and if n is greater than or equal to 1, so that means that they are zeros. But so that x1 is 0, x2 is 0, and xn is 0. Because at the time 0, you have n arrivals. So the first interrupt time is 0, the second interrupt time is 0, right? Up to the nth interrupt is 0. But because x1, x2 up to xn, they are exponential distributed. So they are continuous random variables. So of course, this probability is 0. Okay? So this is 0 for all n prime. So that the probability of n0 equal to 0 is equal to 1. So this is the first property, right? We have. Okay? So this is the first property. Right? And it needs some elaboration to prove that NT has independent increments. Right? And so let's just skip it. Now, since we have the event that the nth arrival time is less than or equal to t, means that n of t greater than or equal to n. Right? So they are equivalent. Okay? They are equivalent to each other. So, because that, you see, the nth arrival, the arrival time is less than t. So that means that in the time interval from 0 to t, we have at least n arrivals. So that is that they are equivalent to each other. Alright? So from this one, we can prove that the random variable n of t has some distribution. Okay? So we can prove that they have some distribution. Okay? Because that we know xn are gamma distribution with parameter n and the lambda. So I'll just give you an idea, and you are asked to fill up the details. Okay, so once we end up with this distribution, we can compute the increment, right? All right. So the increment. So and therefore the increment, when we compute the increment, we find that the increment is independent of x. So now we have the stationary increment. And also the increment has some distribution with parameter number times. Right. So I just give to you that. Of course, there are some details to complete the proof, but the idea I have given here. So now we get a second way to identify whether a point process is sum or not. Is that to look at the integral terms. So first of all, if there is a point process and we find the integral terms are statistically independent and identity distributed. Alright? So it means that we find that the integral values are RID. This is the first thing. The second thing is that we check whether the integral value is exponentially distributed. If this is also true, then this point process is sum process. So this is the second way to identify whether a point process should be a sum process. Okay, so I think that this is some important properties about the sum processes. Do you have any questions? Okay. All right. So if there's no questions, then I stop here.